In this video, we will look at how principal component analysis, PCA, can be used for dimensionality reduction. So let's first describe the task of dimensionality reduction, which is a form of unsupervised learning. Consider the situation we have some two-dimensional data. It is clear that all my data points are close to this straight red line. Hence, we want to simplify the way we represent our data by just using a single number in place of two dimensions. So in this example, a point 34 in the original space can be mapped to a single value of 5 in the dimensionally reduced space. The red line is what we call a linear manifold, and dimensionality reduction only works well if all our data is close to a linear manifold. PCA is the method by which we find the direction of the red line mathematically from our data. Okay, let's find this red line direction mathematically. We have some data. In this case, we have n data points, and the dimensionality of each data point is something big. We want to make a transformation where the original data is mapped to a space which can be defined by a single scalar value, u. So we introduce this weights vector to linearly transform from x to u. This weights vector is what we want to learn from PCA, as it will allow us to find the space u. So the best w is basically the one which maximizes the variance of u over all of our data. This intuitively makes sense, as the direction along the u direction, i.e. the red line, is the one where the data is the most spread out. We will make the assumption that the average of all of our data points in the original space x is 0, which in turn means the average of the data points in the u space will also be 0. This assumption will help make our maths easier, and it's not really a big deal, because if we have data with a non-zero mean, we could just subtract the mean from each data point before doing PCA, and then just add back the mean at the end. So for each data point, we can say un equals w transposed xn, and mathematically, the best w, which I will call w star, is the weights vector that maximizes the variance of the variable u. If the mean is 0, we can say the variance is simply the expectation of u squared, and we can write this in terms of all of our data points in terms of un. So far, it's quite hard to see how we maximize this expression. So let's try and simplify it by substituting in un equals w transposed xn. By expanding the square and flipping the second term because it's just a scalar, we get this. As the w's are not a function of small n, we can move them outside the summation. This expression in the brackets has a special name, as it is the covariance matrix for our data. So we want to maximize w transpose c w over all possible values of w. But obviously, we can make this expression huge by just choosing a value of w that has a large magnitude. But we are not actually interested in the magnitude of w, and only in its direction. So we introduce a constraint to restrict ourselves to directions with unit norm. The way to maximize an expression with equality constraints is to introduce a Lagrange multiplier. If you're not familiar with Lagrange multipliers, just Google it. The easiest way to find the value of w that maximizes this expression is by differentiating with respect to the vector w and setting the expression equal to 0. And after differentiating and rearranging, we get the solution Cw equals lambda w. Therefore, w star is the eigenvector that corresponds to the greatest eigenvalue of the covariance matrix C. Note, the maths we have done here can easily be extended for the case our dimensionally reduced space u is not a scalar value, but something with more dimensions.